Thank you, Sylvie. Okay, thank you for the invitation and to the organizer for this really nice workshop and school. I will talk about some formulas of cumulant-to-moment relation related in part with the Frédéric talk and also the Adriano's talk. So for the background, I will try to recall what it was say about non-commutative probability space. So I will define it directly, okay? A non-commutative probability space for me will be just a pair of formed by a unital associative algebra over C or R. So let's take the complex and a linear functional, sending 1 to 1. There are several notions of independence in the non-commutative setting, which is in fact, one of the motivations to take a look to the non-commutative, this non-commutative approach. So three important ones are the freely Boolean and monotone independence relation. Okay. And in order to understand this relation, again, in the non-commutative setting, one important combinatorial object is the non-crossing partition, which I recall the definition here. So what we are looking for is for set partitions such that we have this condition, meaning that there's no pair of blocks which intersect. Essentially this condition said that the integers on the blocks bi and the integers on the block bj will not cross under that condition. Okay, so there are several types of non-crossing partitions. So here are two that we are going to use. The one is the irreducible non-crossing partitions, which are the ones such that the first and the last element are related. That is, they belong to the same block. And interval non-crossing partition, which are those non-crossing partitions such that the elements on each block are consecutive integers. Another notion that we will use is the notion of nesting. So two blocks on a non-crossing partition, one block in a non-crossing partition is netted into another one if every time we take two elements, B1 and B2 in B, for every B prime in the block B prime, there exists B1 and B2 in B such that we have this property. And from the nesting, this definition of nesting, the nesting notion, we can define a special planar tree called the tree of nesting of an irreducible non-crossing partition, which essentially encodes the hierarchy of the nested blocks of pi. And then we can extend this map to all non-crossing partition by just the following observation is that every non-crossing partition can be written as a concatenation of interval non-crossing partition, just taking into account the set over which interval non-crossing partition is defined. So here's an example of what I'm saying. We have a non-crossing, so this non-crossing partition of the set 18 can be seen as the concatenation of two irreducible non-crossing partition. The first one, a non-crossing partition of the set 1 to 10, and the other one considered as a non-crossing partition of the set 11 to 18. And okay, so and here, so there's an example of the hierarchy tree that we are looking for. So notice that, so for each irreducible non-crossing partition, we have one planar tree associated, and then when we have any non-crossing partition, so what we have is a ordered forest of planar trees. There is also a notion, let me recall the notion of tree factorial, defined recursively like this, using the notion of grafting of an ordered forest to a root. Okay. So back to the non-commutative probability space. Let me finish with this notation. Every time that we have a family of multilinear functional and a non-crossing partition, f of f sub pi will be this product of f sub the length of the block B, and if B, writing B in a increasing way, then the argument on the function phi sub the cardinal of B, the argument is the B1, B2 on onto BR. So again, for our example, if the pi represent this non-crossing partition, then f pi of the argument A1 until A9 is this product, okay? So we have in the setting of non-commutative probability space these three special multilinear functional, which are the free cumulant, the Boolean cumulant, and monotone cumulant, defined via this relation. And one problem, or one interesting thing to see, is how the cumulant are related between them, and if it is also possible to have formulas which express these cumulants now in terms of the moment phi. This has been done in the last years. And what I want to show you is a couple of formulas for the free and Boolean cumulant in terms of the moment using a Prelli approach. Let me also mention that for the first two formulas, so the first one is over non-crossing partition, the second one is over non-crossing interval partition. So notice that in the third one we have this coefficient, and for the first two we can see those sum over the poset of non-crossing partition, and this allows to apply Möbius inversion. Okay, for the third one it's not so easy. So let me tell you what is this approach and explain you why is this image of Alice in Wonderland. So the approach, let me remind this Ebrahimi-Fard and Patras really nice way to see cumulant as infinitesimal character of some Hopf algebra. So here, let me go out from the non-commutative space A and just work with a vector space V. So we have the tensor algebra on V and the reduce. So essentially the tensor model and reduced tensor model, these two are vector space. And I'm gonna consider, we consider the space T of T plus V, okay? So in T of V, normally there is a product and coproduct formula which come from the concatenation and the shuffling, but this is not exactly the product and coproduct that we're going to use here. So first, let me say that consider this graduation, and I will looking at elements on homogeneous of degree n as words on words. Okay, so I will, so letter are words, and I'm concatenating word after word, and to separate the words from the words on words, I will put a bar. So the bar here is represent the tensor in T of T of V. Sorry? Oh, sorry, it's direct sum, yes, sorry. sorry, yes. All right, so what are the product? So we will form a Hopf algebra here. What are the product and the coproduct? The product is simply the concatenation of word on words, and the coproduct is given by this operator delta, which I wrote maybe too fast, but what's happening here is that we can first define delta for any word. So you have ABC. It's a sum over all the possible choices of letter of U. So we can have, for example, if I choose, so here n equal 3, if I choose the set 2, so and this is U. So I'm restricting U to the set A, meaning that I'm taking the second letter, B, tensor, and then by this UK1 bar UKR, what I mean is I'm looking at the complement of A in N and then taking the intervals in there. I will have the intervals in the complement. I will look at the subwords of U given by these positions. And every time there is a gap between one interval and another, I put in a bar. So here I have just two intervals, which is formed by the singleton 1 and singleton 3. And because there is a gap there, then I put a bar. So this operator delta is gives you a sum of tensor, where the left tensor is a word and the right tensor is a word on word. And what we, to complete the definition, we just extend multiplicatively delta. But Ebrahimi-Fard and Patras prove that with this product and coproduct, we have a bialgebra, and because it is connected and graded, automatically we have a Hopf algebra. Moreover, from the coproduct, we can define two special operators, which are the left and right half coproduct, which is the same as delta, but taking into account if one lives or not in my subset. So there is a typo, it should be A instead of S, sorry. And with this two half operation, the double Hopf algebra has a codendriform bialgebra structure, also called on shuffle. This is also unital. Now, once we have this double tensor bialgebra, we will consider the space of linear maps from the double tensor algebra to the field. And we consider these three operations. The first one is the normal convolution product, and the second and third one are the ones, the convolution defined from the half product. I'm not going to define strictly what are dendriform and codendriform spaces, but let me just say that from a dendriform algebra, we obtain automatically a Prelli structure, but just defining the Prelli operation like this. Oh, yeah, okay. Yeah. Thank you. What? Well, change the sign? uh, so this is a pretty, well, which one is? Estas. Ah, okay, thank you. Thank you. Gracias. All right. Huh? It's still wrong? It's what I wrote before. No? Well. Let me continue. And all right. So we have the double tensor algebra. We consider the group-like set of group-like elements, which is a group with respect to the convolution, and the inverse of this group can be calculated via the antipode. We also have the infinitesimal character set, which is a Lie algebra with a Lie bracket defined by the commutator inside LV. Now, going back to the non-commutative probability space, if I now let's do all this construction with A instead of V. So the multivariate moment for a word in the n tensor of A is defined like that, and then it is extended from the linear form included in the non-commutative probability space to a map from the double tensor algebra to K. So Ebrahimi-Fard and Patras shows that if we consider the exponential constructed from these three operations, the convolution and the two half convolution, the solution of these three identities correspond to monotone cumulant, monotone free and boolean cumulant. Okay. So it is a way to look at the cumulant as infinitesimal character in this particular Hopf algebra. Now, also, so for the exponential, for the convolution exponential, the first one, we have an inverse, which is the logarithm. But for the second and third, which are time exponential maps, there is a notion of time logarithmic map, which I'm not, I will not precise, but it's essentially these two identities here, which are satisfied by kappa, beta, and the moment phi. So this just says that if we know the inverse of phi, we can have a formula for kappa and beta, and this is what I will look at. What can we obtain if we go through the inverse of phi to calculate kappa and beta? So that's why I'm looking this as looking at the other side of the mirror. How is my time? Okay, I'm almost done. So in order to give a formula for the antipode, I will need the notion of set compositions, which are set partition, but now with an order in the set of a total order in the set of the blocks. I will write a set composition. I will distinguish a block and the consecutive one with a bar, which is a notation, similar notation of what happened in the double tensor algebra, but it is a coincidence. It's just in these two words they use the same notation. Set compositions appears in several notions. Let me just say that when we consider flags on subset of n, this is essentially looking for a set composition. And this point of view is important for the formula of the antipode. So also, if I have a word, I'm going to consider, and for every word and every set composition, I'm going to define, a new word, a word-on-word obtained by looking at the restriction of the word on every block and then not putting a bar every time we have a bar in the set composition, but instead we will follow the following rule. So when I restrict my word to the first block of the set composition, nothing happens. But when we restrict the word to the other blocks of the set composition, if inside the block, if the block is not an interval, we put a bar to distinguish when there is gaps, okay? So for instance, for this word u of length 9, I restrict u to the first block, so it's A2, A5, A6, that's okay. I put a bar, then for the second block is A9, nothing happened, but for the third block, we have a gap here, so between 1 and 3, and between 4 and 7. 3 and 4 are consecutive, so I put a bar between A1 and A3 and 4, and between A3, 4 and A7. Okay? I'm going to also, this is the last notion before presenting the formula. If we have a set composition, we will say that the set composition have a consecutive interval property if all the blocks in my set composition are interval, but the first, okay, so no condition on the first one, and if the maximum of a block is smaller than the minimum of the next one, the union of both blocks is an interval. And we call NC with a arrow the set of set composition with this property. So here's an example. The first one is not, of course, a non-crossing consecutive interval because we have a crossing. The second one is neither a consecutive interval, have the consecutive interval property because the second block there is a gap between the second block and the third block. Okay, and the third one is an example. On the left, I'm putting another way to see this non-crossing partition. So let me just say a last word about calculation of the antipode. So this is the general formula that we have from this is called the Cauchy's formula. It involves a lot of cancellation. For instance, if we want to calculate the antipode of the word A bar BCD, so these have 75 terms, which will reduce to 11. So it is good to have a non-cancellation formula for the antipode in the sense that it gives you efficiently the image of an element, also for programmation reasons. Okay, so the formula for the antipode in the double tensor algebra is given by these non-crossing interval set compositions time this sign, and this is a cancellation-free and grouping-free formula. So in the last minute, let's apply this formula to the relation between these two cumulants, the kappa and beta cumulants. So recall that we have this relation. So this gives you these two formulas for the kappa cumulant and beta cumulant. Okay, in terms of this non-crossing set composition, non-crossing set interval compositions. Also, going back to the Frederick's talk, who talked about weak map, the free weak map, considered by Ebrahimi-Fard, Patras, Tapia, and Sambotti, is defined as this convolution between the identity and the inverse of phi. So applying the formula of the antipode, we can write directly the Vig map. We have a formula for the coefficient which appears when we expand the Vig map like this. Okay. So to finish, there is, as you know, there is a lot of formulation, as I said before, between cumulant and moment, cumulant to cumulant, and because now the formula, the cancellative formula for the antipode involve this set composition with the interval property. It seemed to have some relation between the poset of non-crossing partition and this particular set. And also, let me say that for the Arismendi-Celestino formula of cumulant-to-moment formula, that formula involves the Murray's coefficient, and we conjecture that in fact those coefficients can be parametrized by chains on the poset of non-crossing partition. So this is work in progress, and thank you very much.
Nice talk. Are there questions, comments? Can you say more about what you expect to deduce from these new formulae?
Well, first is that we don't have the non-crossing. I mean these new objects are not evident from the classical approach, right? So what I'm interested to do in a combinatorial sense is to see the relations between these new objects and the classical one which appears in the classical expansions. Well, at least combinatorially see which property have this object inside the non-crossing partition, which is essentially the main object used here. Yeah.
Do you have a way to deduce the nesting tree of the Krepler's complement in terms of the nesting tree of the original non-crossing partition?
So the nesting tree of the? No. No. I will have to think about it, but not at the moment, no. It would be nice to make a link, yeah. Thank you.